All right. So what we're going to talk about now is has a lot to do with the process of statistics. So we want to talk about how that works here. What do we mean when we say the process of statistics?
Using a sample to understand the population.
Okay, so we're going to use the sample to understand the population. Why do we use samples? Why don't we just measure the population of stuff? It's impossible. Why?
There's a lot of people out there.
There's too many people in populations usually. So if I want to say something like, I want to know, let's just say, the height of 3-year-olds in lacrosse. It's going to be hard for me to actually get a hold of all the 3-year-olds in lacrosse and measure their height. Okay? But I can probably get a sample if I somehow randomly select 3-year-olds. Now, it might not be great because I might not have access to all the 3-year-olds in lacrosse. So I might have to do some convenient sampling, which might be biased in some ways. But at the very least, it's going to be impossible for me to get everybody, most likely. So I'm going to try and get a smaller group, a sample, and I'm going to try to do the best I can to have it be relatively random, to pick a group that I'm going to work with. But as we know, this creates something called sample variation. Or sampling variation. And that means the numbers change because we're doing samples. If I picked 20 high school students in a sample and I did a study, and then I said, okay, see you later, and then I picked another 20 high school students, my numbers would be different. So I'm going to have sampling variation whenever I do something that uses samples. But sampling variation can be partially controlled so that we can actually say, I'm going to have a mathematical idea that's going to tell me how much variation I should expect in a sample. It's really important because I want to understand the population. If I can get an accurate sample, then I'll be able to say something meaningful about the population. But if my samples are just way out of craziness, then I'm not going to be able to figure anything out. So what we're going to deal with right now is sampling variation. We're going to talk about how that works and how we might be able to understand it and then work with it in order to be able to make decisions and figure out what's going on. So what I'm going to do is I'm going to create 3 different data sets, and I'm going to describe them, and I'm going to go all the way across here to this right. Okay, so that you know what's going to happen. I'm going to start, I'm going to go all the way across, and I'm going to come back here, and I'm going to go all the way across. The third one is not that big of a deal, but the first one and the second one are pretty important. Okay, so how do I start this? I start by talking about a bell-shaped population. And we're going to use the height of 3-year-olds. And what we're going to say is that I have a mean equal to 95 centimeters and a standard deviation equal to 4. And I actually looked this up, so I think it's really good, except I don't have a feeling for how much a centimeter is. So that makes it a little bit not work very well. But if I say a centimeter, well, it's like, I don't know, 2/5 of an inch or something like that. So then this would be something like 40 or 36 inches, somewhere. Okay, not like that. Okay, so then when I say, what does this actually look like? What I'm going to do is do kind of a dot plot here of that population. It's bell-shaped, okay? So that means it's big in the middle and it comes down either side symmetrical. The middle of this is 95. And then I ask the question, what to expect? And I'm going to use the empirical rule. Based on this situation with these numbers, can you tell me, based on the empirical rule, what I would expect any particular 3-year-old to be in terms of height? What does the empirical rule tell me in this situation? What that means is that you know what the empirical rule is, and you have your calculator out, and you're using it to find the numbers that I want to know for this particular situation. Katie Larkin, you got something for me? Okay, Mariah got something for me?
Arguing 95 minus 2 times 4.
Yes.
Okay, so that is 87.
Okay. What else do I want to do?
95 plus 2 multiplied by 4, which is 103.
Okay, and so what does the empirical rule tell me?
If it's less than 87 or more than 103, it's unusual.
Okay, so then I would expect it to be between these two numbers. And if anything outside of there, I'd be surprised. Okay. So I should probably take out a couple of these X's here. These are surprises. Okay. Now, the next question that we ask is, what happens when I take a sample? What if I take a sample? The first thing that I want to get from here is I want to know my sample size. And so I'm going to say n is equal to 25. So if n is equal to 25, then that means I'm going to, since I don't have access to all the 3-year-olds in the city, I'm going to somehow randomly pick 25 3-year-olds and measure their height. And then the question that we ask is, what happens when I do that? What do I expect to happen when I take these samples? And if I have something that looks like this, and I have a 95 in the middle, will I get 95 from every one of my samples? No. will I get some, if I do this, and I take 25 and I throw them back in the pond, and then I take 25 more and throw them back. I take these different sets of 25. Will I have some averages if I take the average of those 25? Will I have some averages which are below and some which are above? Everybody else says that makes sense. But it also makes sense that the average of the averages would be 95. Remember, X bar represents the sample mean. And remember over here, mu is equal to 95, which is the population. Can somebody tell me what's the symbol for the standard deviation of the population? Okay, yes, that thing that I didn't want you to say, that's right. The O with a tail on it, which is a small sigma. That's sigma. That's 4. Okay, so I know, and this is how I'm working with this, okay? I am telling you that the population mean is 95 and the standard deviation is 4. Okay, you have to know that in order to do the rest of this stuff, okay? But if I know that the population mean is 95, then it looks at when I say, I want to find the average of these 25 little children. And I say, hey, little children, there are 25 of you. I want to find your average height. And I find it. It's not going to be exactly 95. Sometimes it'll be higher, sometimes it'll be lower. But I would think that the average of those numbers would also be 95, even though it's not exactly accurate. So how I write this is the mean of X bar is equal to 95. So the mean of the averages is the same as the mean of the population. It just seems to make sense that that would be true. However, when I have this in my mind and I say, I know what this average looks like, the big question is, what does that standard deviation look like? What is the standard deviation of these averages? Well, let's go back and look at this thing right here. If I'm choosing 25 different children, it would not make sense that they would all be bigger than 103, or that they would all be smaller than 87. If I'm actually choosing 25 children at random, then that means that I should have less of a spread for these numbers compared to the actual population data. It's certainly true that one child could be higher than 103 centimeters. But it would not make sense that I would get all 25 children that could be taller than 103. So what happens here is that this, which is called the sampling distribution, okay? This thing here, which is called the sampling distribution, will have a smaller standard deviation compared to the data itself. And what does this look like? Here's a formula. Standard deviation divided by the square root of n. So this is what happens. We have a mathematical formula that tells us how much smaller is the standard deviation. when I'm talking about taking a sample of children, some of those samples will be high, some will be low, but the standard deviation of those numbers will be less than the standard deviation of the original data set. So what would that be for us right here? This would be 4 divided by the square root of 25. So what do I get for a number when I do that?
Mhm.
0.8. So what does the empirical rule tell me about what to expect in this situation? If I use the empirical rule, what are the intervals that it tells me about my results? I want to use the empirical rule to figure out what these numbers are. Now, it's unfortunate that a number of you are saying, well, somebody else is going to do this for me. Well, maybe they will, but it would be nice if you know how to do this yourself. Okay? If I have a mean of 95 and I have a standard deviation of 0.8, what number should I put in here using the empirical rule to know what's the interval that I would expect to happen? I want to know that. And I would like for you to be able to do this on your own calculator. Alex, you got numbers for me?
Just a minute.
Okay.
The first one I got 93.4, so
Okay, 93.4 on the side.
and then 96.6.
And 96.6 on this side. So what this is telling me is, when I have these 25 children walk into the room and I find the average of their heights, if it comes out to be 97, I'm surprised. Because if I'm getting a sample of 25 children, then I expect that sample number to be between 93.4 and 96.6. So if it's 97, I've got a bunch of tall children in my sample. Whereas over here, 97 for an individual child, that's not a surprise at all. 104, now that would be a surprise. 97? No. So when I take a sample of 25 children, it's reducing the variation and it's increasing then the accuracy of what I can expect to happen. So my sample averages are between this relatively small interval right here. All right. But then comes what they call payoff. Does anybody have any questions so far? Okay. So then we have something called the central limit theorem. The central limit theorem says to us X bar is bell-shaped. So it's not just that our data set originally was bell-shaped, but we can specifically say that this is a bell-shaped distribution according to this central limit theorem. That if we take samples, some will be higher, some will be lower. The mean is the same as the data. The standard deviation is smaller according to this formula. And these are now bell-shaped. So that means we can create z-scores for this. So if I ask this question, what is the probability of having a sample mean larger than 96? So this is going to use my z-scores, just like what I was doing before, except the mean is 95, the standard deviation will be this 0.8. So here's what that looks like. Here's my, I have 95 in the middle, I have 96 out here, and I want to know what that area would be out there. So if I want to find this area, what's my next step going to be? I want to find the area which is greater than 96. What's my first step in trying to find area like this?
Data value minus the mean divided by standard deviation.
Okay, I'm going to make a z-score. That's what I'm going to do, right? So I want the z-score, and in this case, it would be 96 minus 95 divided by 0.8. Okay. So I'm going to figure out what the z-score is for that number. It's 1.25. Alyssa, can you tell me what to do with this number, 1.25? Okay. Sierra, can you tell me what to do with this number, 1.25? Okay. Elena in the second row, can you tell me what to do with this number, 1.25? Okay. Mara, can you tell me what to do with this number, 1.25?
You look on table E,
I do.
and then you go to 1.2, and then 0.05, and you get 0.8944.
All right, and then what do I do with that number?
1 minus.
1 minus that number. Yes, I do. What do I get when I do that?
0.1056.
0.56, is that what you're saying?
Yes.
So this is 4.
8944.
8, 9. 4.
Yeah.
Okay. So, what needs to happen to make this work? The first thing that happens is that I recognize that I'm talking about a sample mean. I'm taking a sample. I'm no longer talking about the individual data. I'm looking at a homework problem that says, and a test question that says, sample mean, or average of the samples. So I'm not just talking about an individual person, I'm looking at taking a sample and finding the average. And so I have a sample size, in this case, n was 25. I have my mean, mu is equal to 95. I have my standard deviation, sigma was equal to 4. But then this thing down on the bottom is not a 4. Because this thing right here is sigma over the square root of n. So I'm taking the standard deviation from my data set, dividing it by the square root of n, and that's the number that goes on the bottom of this fraction. Because I'm talking about a sample, then that's what's happening here. Question?
So this question would always come after the sample question, right? So it would follow it?
Okay, all that has to happen here is that this question has to say sample.
But then like the n of 25 was on the last question.
Okay, n of 25 could be in this question, okay? So it would have to be told to you. I would have to make sure you know what is the size of the sample in order to be able to figure this out. Okay. So right here, I know I have a sample. I know it's 25 children. I'm finding the average of their height. And I want to know, should I expect the average to be greater than 96 for these 25 children? Well, it could be. 10% chance. Okay, I would not be surprised. But it's not the most likely thing, but yeah, it could happen. So again, what's going on here is that I have to be told all the population information, and then based on that, I can have an idea of what samples will do. What can I expect to happen? Okay. Now, this was for a bell-shaped population. I want to do the same kind of a process, but now I'm going to do it with a population which is not bell-shaped. So, I can use red. Thanks, red marker. That one's going. I'm going to go through a similar process with this, but now I'm going to have something that's not bell-shaped. Not. So let's say that I'm talking about the commuting distance for parents. I've been talking about children, might as well talk about parents. So let's say we're talking about the commute distance. How far do people have to travel to get to my child care facility or whatever? 0, 10, 20, 30. This is the number of miles, okay? And I'm going to put a bunch of X's here. Is it possible for people to travel 30 miles to get to La Crosse in order to work? Okay. Is it likely that people would travel less than that? Are there a lot of people who actually live in La Crosse and work in La Crosse? Yeah. Okay. So if I look at this right here, I've got a lot of people that are less than 10 miles away from wherever they are. But I do have some people that are 30 miles away. This is not bell-shaped. So what I'm going to say here is that the mean is equal to, let's say, 8. And the standard deviation is going to be equal to, let's say, 5. Well, no. Let's say 6. This is not bell-shaped. So if I try to do the empirical rule over here, it doesn't work. Because it's right skewed, it's going to look something like this maybe. Okay. But what happens when I take a sample? And let's do the same sample size. N is equal to 25. What will happen when I ask 25 different people, how far do you live away from your job? They're not all going to say 30 miles. In fact, most of them won't say 30 miles because most people are pretty close to where they work. Some people will, but most of them will not. As it turns out, it'll look like this. 8, which is the actual mean of the data set, will also be the mean of these averages. So when I have these 25 people and I say, okay, how far away do you live? And I find the average of them, and I say, okay, see you later. 25 more people walk in. I say, okay, what's the average for these 25? Okay, now you go. I do this over and over again. Sometimes it's higher than 8, sometimes it's lower than 8, but the average of these averages, again, the mean of the sample means is going to be 8, the same as the mean of the data. It's not accurate in that it doesn't exactly tell me what the population average is, but sometimes it's higher, sometimes it's lower. If I do it, the average of the averages comes out to be 8. However, the standard deviation of these averages will again be smaller than the standard deviation was over there with the data itself. So this is going to be sigma divided by square root of n, which will now be 6 over the square root of 25. So what's that?
1.2.
1.2. Now I'm going to do the empirical rule, and I want to know what I can expect from my averages now. So I have a mean of 8, I have a standard deviation of 1.2, and I want to know what that's going to do. So, Abigail, can you tell me what I would get from the empirical rule for these numbers? Well, how about 90 seconds? Oh, no. Okay. Hunter, how about you?
I gotta do the same thing so fast.
All right, you're gonna pass, all right. Jessica?
For 8 plus 2 times 1.2, I got 10.4.
10.4 on this side?
And then for 8 minus 2 times 1.2, I got 5.6.
5.6. Okay. So Jessica gets an extra gold star today. So now this is telling me I have a reasonable interval. So when I get 25 people and I sit them down and I say, how far away do you live from work? And I find the average. It should be somewhere between 5.6 miles and 10.4. Is it possible somebody can drive 30 miles? It certainly is. But it's not really possible for that to be the average of 25 people, assuming that these numbers are correct. So that when you say, okay, everybody who lives in La Crosse or works in La Crosse, everybody that works in La Crosse, I randomly pick 25 people. They don't all live 30 miles away. But they also don't all live next door. So there's some kind of a reasonable interval that I would expect this 25 average to be. So, but that's the next thing. The central limit theorem right here. The central limits theorem says, central limit theorem X bar is bell-shaped if n is large. Here we go.
What's large?
Means bigger than something else. Statistically, we generally say this number is somewhere around 25. Some textbooks go for 30, but it doesn't really track exactly.
Okay.
If our original distribution was crazy, weird, gotta be kidding me, scattered all over everything, then we might have to go with 50 or 100. But most of the time, most data sets are kind of bell-shaped. And so 25 is usually a decent number. Some textbooks say 30, some say 40. But it really depends on what your data looks like originally. So if you have a large enough sample, then you can use bell-shaped ideas to analyze what to expect. And it goes back to Plinko, really. Remember, in Plinko, you could go either to the left or to the right, but you had pretty much an equal chance of going either way. Well, the same thing is true if you're picking people at random from this data set over here on the left. Some will be smaller, some will be greater, but it'll kind of average out. Because if you're picking them by randomness, a lot of them are going to be kind of in the middle. They're not all going to be one way or the other. So this works. So that means I can do the same process with this information that I could do with the height of the 3-year-olds. So what is the probability of having a sample mean smaller than 6? So let's see if you can make that work. All right, so ask your neighbor if they can explain it to you, or explain it to your neighbor if you already know how to get this, all right?
Oh, it's like they came back. 6
Yeah, because it's 6 minus 8 over our sensitivity is 1.2. Negative 1.67.
How did they get?
Like that, but I'm like, yeah. Like it's the same.
All right, Casey, what do you got for me?
So I took 8 minus 6 divided by 1.2.
Actually, we want to take 6 minus 8. Because the data value, here, the sample mean we're interested in is 6. The overall mean is 8. So it'd be negative, yes. And what would that number be? Negative what?
1.6.
We want 2 decimal places here. So negative 1.67 then is what we'd be looking for. And so then here we would have negative 1.67, we want less than that. And again, this would correspond to saying, here's 8 in the middle, here's 6 over here, we want less than that. So this is X bar, this would be Z. So we're looking at averages less than 6. And so we're looking at Z scores less than negative 1.6. Okay. All right. Loanne, you got a number for that? Okay. Negative 1.67. We want to figure out what area corresponds to that Z score. Tia, can you tell me how to find that?
Yeah, you go on the chart and then you go over to negative 1.6 and go over to 7. That's 0.0475.
0.0475, yes, that's right. This would be our area or the probability. So would we be surprised by this? Yeah, pretty much. So we're looking at this and we're saying, wow, does it make sense if I'm doing a survey and I have 25 people and they tell me on average that their commuting distance is less than 6 miles? It's like, oh, that's kind of an unusual event. I am surprised. I have a bunch of people that live relatively close to their jobs. Okay, that would be an unusual event. All right, so this happens for bell-shaped data, but it also happens for not bell-shaped data, which means then I don't have to know what my population data looks like in order to know what my samples are going to look like. And I can, in a sense, verify the accuracy of my samples because I can have an idea of what is a high and a low sample, and I don't have to know what the population data looks like in order to find an unusual event for a sample. So I can take a group of people and I can say, well, you guys are a lot closer than what I expected you to be, without knowing that it's bell-shaped with my original data. And that's really good because I don't always know this, right? Now, this being the case, all right, having this information is good, but there's another set of information. And I'm just going to show you how this works. And that is for asking yes or no questions. What happens if I just ask a yes or no question? Well, I'm going to get some kind of a response, right? And I will get a sample proportion. We already talked about this before. P hat is x over n. So then this will tell me I have a certain sample of opinions or whatever, yes or no. Have you ever heard of movie Armageddon? Yeah. Did you ever watch the movie Armageddon? Okay, so then you can say yes or no. And so then you'd come up with this sample proportion. Well, but this is not accurate, remember? Because this is just a sample. We're not asking everybody. Oh, I should have said the movie Twister. That would be much more, much more popular, right? Okay, so whatever movie you're gonna say, maybe I should have gone with Captain Marvel, maybe or something.
Yeah.
Or up to date. Or Casablanca. There we go. Yeah, okay. So anyway, when you watch this movie, either you watched it or you haven't. So then that would be a sample based on whoever I'm talking to, right? Well, these samples are not going to be exact compared to what the actual number is. So once again, I'm going to have sample p hats that are going to be above and below the actual general probability. Remember we talked about that, okay? So it's not exactly the same as the general probability. It's above and below this general probability. So then I'm going to have the same process here where I can use these mathematical formulas to, in a sense, predict how accurate this number is. And so it might be higher, it might be lower, but there are mathematical formulas to tell me how accurate this will be. Now your textbook doesn't actually go through this, so we're not gonna. But it's gonna come up later. There's a formula that we're going to have, and it's going to have that thing in it. And so you'll need to be able to see that. But what this requires of you, okay, is that whenever you're going through a homework problem and you see that it refers to the sample mean, then your formula is not going to be exactly the same as it was before. So it's going to look like this. Z is equal to x bar minus mu over sigma divided by the square root of n. That's going to be the formula for finding z-scores when we're talking about the sample mean. And obviously, from what we did before, you have to do this part, sigma divided by square root of n. This has to be separate from the numerator. The numerator has to be done separately from the denominator. So you do the top of the fraction, find out what that is. Do the bottom of the fraction, find out what that is, and you divide, get your number. Okay? But the beauty of this, okay, hopefully you get this. The beauty of this is if I can control my sample size, then I can control the accuracy of my information. So that I can say something like, I want to have a certain level of accuracy when I do this. Well, then that means I need to talk to 300 people or 1,000 patients or something. But then I will be able to control the accuracy because the bigger this number is down here, the bigger this sample size, then the more accurate these samples are going to become. And so I will be able to know how confident or how much truth is in my statements because I will know how much of this is varied, how far up and down this number goes. So then I'll be able to say, I can trust this number. Because if I have a large sample size, it will make my calculations more accurate. Well, it sounds good, all right? It sounds good. But in practical terms, remember, we don't know if there's confounding variables out there. We don't know what kind of weirdo stuff is happening. We have to be humble about what we're doing. There are going to be things that change our answer. We could, measure 100,000 people and they would all be strange for some reason because they have telephones or something, whatever. This doesn't always work, but it is a way for us to control the sampling variation so that we can actually know what to expect. And if something weird happens, then we say, hey, these people have more lead in their bloodstream, or these people have a problem with this kind of nutrition or whatever, because we know how to handle this kind of situation. All right, that's enough for today. And I will plan to see you on Tuesday.